So what makes a proton donor then? You have a more stable conjugate base, okay? You look at the conjugate base. If you want to compare strengths of acids, compare the conjugate base. What did we know about the conjugate acid-base pair? Remember, Ka times Kb is 10 to the negative 14, right? The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. So compare the conjugate bases, because those are because once you get those compared, then you can predict what the comparison is for the acid. Okay. In general, okay, if you can look at the structure of your conjugate base and see that it is more stable, the more stable your conjugate base is, okay, the weaker that base is. What that means is it's less likely to hold on to a proton. It would rather be by itself. It has a greater tendency of just being by itself because it's more stable. So it has lesser tendency to accept a proton. Okay? So a more stable conjugate base gives you a weaker base. It will have a stronger conjugate acid. Okay. So let's take a look at an example. What we need to look at to determine the stability of the conjugate base. Most bases, as you realize, are negatively charged, right? So basically, the lower the charge density, in other words, the more spread out that charge is. So you're literally looking at the charge to size ratio. Okay? So the lower that charge to size ratio is, the more spread out the charge is, the greater the charge dispersal is, the more stable the base. That sort of makes sense because you don't want to cram all of those charged particles in a smaller volume. The more spread out they are, you have a more stable base, and you'll get a lower Kb. Okay, lower Kb, it's a weaker base. So let's compare fluoride, chloride, bromide, and iodide. Which of these is most stable? What do you know about the trend in size? They all have negative charge, right? So as far as charge is concerned, it's the same. Going down a column in a periodic table, what happens to the size? As you go from fluoride, chloride, bromide, and iodide. Increases, right? So what happens to the charge density? You're getting bigger size. The charge is more spread out. You have a greater charge density. Lower charge density. So which one has the lowest charge density? Iodide has the lowest charge density, right? So which of these bases is the most stable? The one with the lower charge density. So iodide is. Okay? So which one is the strongest acid? Let's see if you remember. Click our question. Which of the acids would be the strongest? HF, HCl, HBr, or HI? This is A, B, C, D, okay? Okay. D. Okay, lower Kb means what? Most stable means weakest base, right? And the weakest base will have the strongest conjugate acid, so HI. Okay, so in terms of acid strength, HI is the strongest. Which one's the weakest? HF. In fact, what do we know about HCl, HBr, and HI? There are 3 of the 6 strong acids, right? 3 of the 6 known strong acids are HCl, HBr, and HI. Now, HI is stronger than HBr, but if you put them in water, it doesn't matter because they're both, all 3, HCl, HBr, and HI, are stronger than hydronium. Okay, so hydronium is the strongest acid that can exist in water. So anything that's stronger than hydronium will just immediately ionize and will donate a proton to water to give you hydronium. This is known as the leveling effect. So you can't tell in water whether HCl, HBr, or HI is stronger because they're all strong. Okay, it's like saying, you need to lift, let's say, a piece of stone. Okay, so if you're all strong enough to lift the stone, I can't tell which one of you is stronger, right?